Hello everyone, welcome back to Math with Allison. Today we're working in our parametric and polar curve series. So we're going to be talking about how we can find the area of polar curves. So let's go ahead and dive into it. Here's a little reminder of our graph, right? We know that our function is going to be in terms of theta, the angle, and then r, the radius. So the question is, how can we find the area of these kinds of functions? So we know how to find the area of a circle, right? Area is just equal to pi r squared. We also know how to find the area of a slice of a circle, right? That formula is area is equal to 1/2 times the radius squared times the angle theta. Now, the question is, what if we're given a really random curve like this? We have our area is going to be r. We start at a theta value, theta naught, and then we go all the way to theta sub n. So what we could do is we could start breaking this up into little pieces. So let's say we add some theta values in between and we break it up really nice and equally. We can estimate the area, and we can do that by finding the area between each of these little curves. So as you can see, it's going to be a bit of an overestimate, right? Because we're adding some additional area, but it does give us a rough estimate. So let the change in theta be equal to this little guy you can see with that little blue star. So delta theta 1 is going to be equal to theta 1 minus theta naught. And we also have that the radius r is going to be f of theta 1. That's going to be the distance that we're using. And what we're going to do is we're going to do that for every single one of those regions. So the first area is, and we can plug it into our formula, 1/2 f of theta 1 squared times the change in theta. And we can do that for every single one. And we get the estimate of the area is where you just add those three up. So when I add it up, I get the sum from k equals 1 to 3 of 1/2 times f of theta k squared times the change in each theta. Now the issue is that this is not a perfect estimate, right? We're getting a little bit more than what the actual area is going to be. So what we do is we break it up into even smaller pieces. So here I broke it up into super teensy pieces, theta 1, theta 2, theta 3, all the way down to theta n. And what happens is the estimate gets better and better. And what we do with integration is we're just taking the limit as all of these little pieces goes to infinity. We're adding more and more, so that way we get more of a perfect estimate, right? So the area is equal to the limit as n goes to infinity, the summation from k equals 1 to n of our little formula right there. And what happens is this is the definition of an integral. The area is equal to the integral from alpha, where alpha is going to be that very first theta value, and then alpha n is going to be our beta. So we have the integral from alpha to beta of 1/2 times the radius squared times the change in theta. That's our d theta. And so that would just be how we found a normal area. We also know how to find the area between two curves. So let's say we have two curves, f of theta and g of theta. We have g of theta is the smaller radius and f of theta is the larger radius between our angles. Then what we do is we just take that bigger angle, we square it, and we subtract off that smaller angle, right? It's very similar to what we've seen with area between curves. But now what we want to do is go ahead and apply it. So example 1, we want to find the area of f of theta equals 2 cosine of 2 theta, where theta is bounded between 0 and 2 pi. The first thing we got to do is we got to draw this out. So this is a cosine, which tells me that all of my petals are going to happen along the main axes, and it's 2 cosine of theta. So I know my petals are going to go out to a radius of 2. And then we have 2 theta on the inside, which tells us we're going to have a total of 4 petals. So I'm going to have a petal on every single one of my axes. And my petals are going to look something like this. That's not perfect, but we try our best. So we want to know what is the total area of this little guy around here. So we want to find the area of all of these petals added together. So rather than integrating the whole thing, what we could do is we could find the area of one of the petals. And since this is an even function, all we got to do is find the area of a half of one of these, this little guy right here. And so there are 8 halves of the petal, right? And so we get that the area is equal to 8. And then we have our theta value. So we start at a theta value of 0, and then we know we go all the way to pi over 4. And the reason we know that is because 2 times cosine of 2 pi over 4 is equal to 2 cosine of pi over 2. And pi over 2 is going to be equal to 0. So we get 2, or cosine of pi over 2 is equal to 0. We get 2 times 0, which is indeed equal to 0. And so at pi over 4, that is where our petals go back into the origin. So that's why we're integrating between 0 and pi over 4. And now we're just going to plug it into our formula. We get 1/2 f of theta squared, so 2 cosine of 2 theta, quantity squared, times d theta. So now what we're going to go ahead and do is simplify this, right? So here I get 8 times 0 to pi over 4. We have to square that whole thing, so 2 squared is equal to 4 times 1/2 is 2 cosine squared of 2 theta d theta. To integrate cosine squared, we're going to go ahead and plug in the little formula. We get 2 times 1/2, 1 plus cosine of 2 theta, but we have a 2 theta already on the inside, so that's 2 times 2 theta, which is 4 theta, d theta. So that 2 times the 1/2 cancels out, which is super nice. And I don't know why I randomly changed this to pi over 4, who knows, but this is still pi over 4. We end up integrating 1 plus cosine of 4 theta d theta. So let's go ahead and integrate that guy right there. We get the integral of 1 is just equal to theta plus, that becomes sine of 4 theta divided by 4 between 0 and pi over 4. So now we're just going to plug in our bounds. We get 8 times, we're going to do upper first, pi over 4 plus sine. Pi over 4 times 4 is just equal to pi divided by 4 minus, let's go ahead and plug in 0. 0 plus sine of 4 times 0, which is just 0, divided by 4. And most of these turn to 0. Sine of pi is equal to 0, 0, 0. Sine of 0 is equal to 0. So all we get is 8 times pi over 4, which is just equal to 2 pi. And that right there is going to be your answer. So the area of all of these petals is equal to 2 pi. Let's go ahead and try another question. So here we want to consider the circle with radius 1, and then our little curve r is equal to 1 plus cosine of theta. So let's go ahead and draw these out. First we have the circle of radius 1, which is fairly easy to draw. And then we have our little cardioid. So this is going to be 1 plus cosine theta. Since it's cosine of theta, I know it's going to extend along like the x-axis. And then we're going to go to 1 plus 1, which is 2 units right out here. We know that it's going to hit the y-axis at 1 and 1. And it's going to go around like this. Beautiful. So let's go ahead and consider part A. Beautiful. So now let's go ahead and consider part A. We want to find the area of the region inside the circle and inside the cardioid. So in that case, it's going to be where the two little areas intersect, which is going to be this whole thing right here. One way we can find this area is we can just break it up into two separate areas. If I zoom in right here, we are just taking the area of this little half circle right here, and then we're adding this tiny area from the cardioid. So the first place we can start is just finding the area of the half circle. So we know the area of a circle is going to be pi r squared, but in this case we're doing a half circle, so all we got to do is divide it by 2. So when we plug this in, we know the radius is equal to 1, and so we get pi over 2. So we know this little area in purple is equal to pi over 2, and now what we want to do is we want to add the area of that little piece of the cardioid. So to do that, we need to find the angles where we can integrate. First of all, we know this little area right here is just reflected on the other side. So let's just find the area of one of them and multiply it by 2. So I know I'm going to have 2 times, and now we need to find our angles. So our first angle is going to be this point right here, which is going to give us pi over 2. And then we go back to 0, which is going to be this point right here at just our normal pi, right? So I know I'm going to integrate between pi over 2 and pi. And now I'm going to plug in what we know for the formula. 1/2 f of theta squared. So that's going to be 1 plus cosine of theta squared times d theta. And now we got to do some simplification. 2 times 1/2, that cancels out. That's just equal to 1. So now we just have the integral from pi over 2 to pi. And let's go ahead and square that. We get 1 plus 2 cosine of theta plus cosine squared of theta, d theta. And we know to integrate the cosine squared of theta, we got to plug it into that little formula, right? We get 1 plus 2 cosine of theta plus 1/2 plus 1/2 cosine of 2 theta, that little double angle identity. Now we can combine some like terms. We have the integral from pi over 2 to pi. 1 plus 1/2 is just equal to 3/2, and then everything else stays the same. And now we got to go ahead and integrate, right? So this whole thing, this becomes 3 over 2 theta plus 2 sine of theta plus 1/2. That becomes sine of 2 theta divided by 2. If you wanted, we could just simplify this to be a 4 in the denominator. And then we're integrating that between pi over 2 and pi. So now we just got to plug in our bounds, right? So let's go ahead and plug in our upper minus lower. Alrighty, so we know some of these terms goes to 0. Sine of pi is equal to 0. Sine of 2 pi is equal to 0. Sine of pi over 2 is just equal to 1. Sine of pi is equal to 0. So let's go ahead and simplify this a little bit. We get 3 pi over 2. Everything else goes to 0. Minus 3 pi over 4 minus 2. And this right here is equal to, if I multiply that by 2 over 2, we have 6 pi over 4 minus 3 pi over 4, and then that little minus 2. This is 3 pi over 4 minus 2. So our final thing is we got to add these two areas together. So we add the area of the half circle, which is our pi over 2, plus the guy that we have over here, 3 pi over 4 minus 2. We can combine like terms, right? Just multiply that by 2 over 2. We end up getting 2 pi plus 3 pi. That's 5 pi over 4 minus 2. And that right there is going to be our answer. For part B, we want to find the area of the region inside the circle but outside of the cardioid. So let's go ahead and get our drawing. I'm going to erase the area that we already found. Alrighty, so the area we're going to find here is inside the circle but outside of the cardioid, which is going to be this little guy right here. And actually, we don't even need to do any more integration because we already found most of these pieces. We know the area of the whole half circle is just going to be pi over 2. And what we got to do is just subtract, and I'll highlight it, we got to subtract this little region right here, and we already found what that was equal to. That's 3 pi over 4 minus, over 4 minus 2. So if we do that, we get pi over 2, and actually I'll make a common denominator, so 2 pi over 4 minus 3 pi over 4 plus 2. That is 2 minus pi over 4. And that's going to be the area that is inside the circle but outside of the cardioid. And then we have one more example here. We want to find the area bounded between r equals 3 cosine theta and r equals 1 plus cosine of theta. So first, let's go ahead and start off by drawing it. We have 3 cosine of theta. It's just going to be the circle that goes out to 3. So it's going to have a center at 1/2. So that is our circle, 3 cosine theta. I go along the x-axis, and then I have that the circle has the diameter starting at 0 all the way down to 3. And then we want to go ahead and graph the same cardioid, right? So I know I'm going to be right there, and then I'm going to go out to 2, and my cardioid will kind of look like this. Good enough. So we want to find the area bounded between these two regions, and it's just going to be the area that they share, which is going to be that I highlighted in pink. But notice what is happening here. We do need to pay attention to the intersection points. So remember what we're doing when we're finding the area. We're using the radius, which is going to be the distance from the origin to the curve. So notice right there, the radius is going to be 1 plus cosine theta, but our function is going to change. If I try to find this little radius right here, now we're going to our other function, 3 cosine of theta. So I do need to know where our intersection points are so I can calculate those different areas. So to find their intersection points, we're just going to set them equal to one another. So 1 plus cosine of theta is equal to 3 cosine of theta. I'll just subtract over a cosine so we get 2 cosine theta. divide by 2. We get 1/2 is equal to cosine of theta, and we want to know where that occurs. And I just always do it by drawing my triangle. So here we have 1, 2, that must be the square root of 3. So this is the bigger angle, which is pi over 3. So that is going to occur at both, if I draw it in pink, pi over 3 and then negative pi over 3. So that is where our intersection points occur. So let's go ahead and set up our integrals, right? So the first thing I'm going to do is I'm just going to take the area, or I'm going to find the area of just half of it and multiply it by 2, right? So let's just go ahead and do the top half. So here I'm going to do 2 times, and now we're integrating from 0. We're starting at the 0 position all the way to pi over 3. The radius in that is the blue one, which is 1 plus cosine of theta, quantity squared, that's our little cardioid, d theta, plus, and then I actually forgot our 1/2 right here. See, it's good to remember the formula. There's a little 1/2 plus, and then 2 times the integral. And now after pi over 3, all the way until pi over 2, when we go back to the origin, that is going to be our little circle, which is going to be 1/2 3 cosine theta squared d theta. Now we got to do some simplification, right? So those 2's and the 1/2 cancel. So here we have 0 pi over 3. And then we're going to square this. 1 plus 2 cosine theta plus, that's going to be cosine squared theta, d theta, plus, and now that's going to be the integral between pi over 3 and pi over 2. That's going to be 9 cosine squared theta, d theta. So let's go ahead and begin simplifying this by plugging in our double angle identity. 2 cosine of theta plus, and that's going to be 1/2, plus 1/2 cosine of 2 theta, d theta, hello, plus pi over 3 to pi over 2. That's going to be 9/2 plus 9/2 cosine of 2 theta. Put that whole thing in parentheses, d theta. Alrighty, let's go ahead and combine like terms, at least for that first one. 0 and pi over 3. That's just going to be 1 plus 1/2. That's 3/2, and then everything else stays the same. Woofda. Okay, let's go ahead and integrate. So for our first integral, we get 3/2 theta. That's going to become plus 2 sine of theta plus, and I'll just make that sine of 2 theta divided by 2 times 2, which is equal to 4. That whole thing is between 0 and pi over 3. Plus, we'll integrate the other guy, so 9/2 theta plus, we'll do 9 sine of 2 theta divided by 2 times 2, which is equal to 4. And that's between pi over 3 and pi over 2. So, let's go ahead and plug in upper minus lower. Okay, I plugged in upper minus lower. Let's go ahead and begin simplifying. So first of all, those cancels. We get pi over 2 plus, we got to find sine of pi over 3. I'm going to use my little triangle. Pi over 3 has the larger leg opposite from it. That's going to be pi over 6, so that has a smaller leg opposite of it. And we know sine is opposite over hypotenuse, so we get 2 times root 3 over 2 plus, and that's going to be root 3 over 2 divided by 4. And now sine of 0, that's equal to 0, so that works out nicely. That's equal to 0. This whole thing goes to 0, so we can ignore it. Now we get plus, we have, that's going to be 9 pi over 4 plus sine of pi is equal to 0, so that works out nicely. And now actually this is just going to turn into a minus. We get those divide out, you get a 3 on top, so we get minus 3 pi over 2 minus 9 times root 3 over 2 divided by 4. Now we got to combine some like terms, right? So this is 2 pi over 4. 2 pi over 4 plus 9 pi over 4 is 11 pi over 4. That cancels to just be plus root 3. So we'll say plus root 3. This becomes root 3 over 8. Plus 9 pi over 4, we already did that. We need to subtract 3 pi over 2. So I'll write that in terms of 4. That's going to be 6 pi over 4. Minus, that becomes 9 root 3 divided by 8. Okay, 11 pi over 4 minus 6 pi over 4 is just going to be 5 pi over 4. And then we have lots of root 3's happening here. So this is like 8 root 3 over 8. That becomes 9 root 3. And actually that just cancels out. That becomes 9 root 3 over 8 minus 9 root 3 over 8. So all we get is 5 pi over 4. And that right there is our final answer. So that is all I have for us today in this video. If you enjoyed it, I have many more like it, so make sure to check out my playlists. They're linked down below. Otherwise, please give this video a thumbs up and comment other problems or topics you'd like to see. Thanks for watching.